Hello, this lecture will cover pages 29 through 33 of my lecture notes, so please print those pages out and have them in front of you as I present this lecture on resistive circuits, chapter 2D, parallel circuits, and the current divider rule. Starting on page number 29 of your lecture notes, the last lecture we talked about series circuits and their characteristics, and this lecture we talk about parallel circuits, and then we'll put the two together for series parallel. But we're just looking at parallel circuits now. The definition of a parallel circuit is a circuit or portion of a circuit in which the same common voltage appears across two or more elements. And here's examples. Notice here we have a voltage source and we have two resistors. Pretty easy to see that they're in parallel. This side of the resistor is tied to this because that's a common point, and this side of the resistor is tied here, and that's a common point. Here there's three resistors in parallel. Electrically, these are all tied to the same point on the top, and electrically they're all tied to the same point on the bottom. That puts the same common voltage across all those resistors, which is 9 volts in that case. Here's another example, but this is an example of a series parallel circuit. Take a look at this circuit. Do you see that in this circuit the resistance values R2 and R3 are in parallel? Don't let this fool you that this comes across horizontal here. This point is the same common point on both sides of the resistor, and this point is the same common point. This is all one point here. This resistor can be turned from horizontal position and move down to the parallel position, and you'll get the look that you have up here. So if you want to look at, in this case right here, let's do some general resistance calculations on these here. I want you to notice here that if you're over here, if you're up here and you're looking at the total resistance, we want to find the total resistance looking in from the source there. In that case, the total resistance is going to be equal to R1 in parallel with R2. You can write it that way. That's not a true equation. Mathematically, you can't solve that, but the total resistance looking in from this point up here to the right is R1 in parallel with R2. Over here, the total resistance, let's do it this way, the total resistance looking in from the source of EMF right there, that total resistance there is equal to R1 in parallel with R2 in parallel with R3. You could write that as a first equality to get started with your work. Down here though, it's a little bit different. The total resistance here looking in, this has a parallel component and it has a series component. If you look at current, the current goes through R1 and then it has to pass through these two resistors here. So the total resistance looking in from the source down here is a little bit different. Let's write it out here. The total resistance is equal to R2 in parallel with R3. We discussed that. And then once you make that equivalent calculation, you could replace these two. You could get rid of this resistor and replace R2 with this value, whatever it is. We haven't talked about it yet. And then you have to add R1. So the total resistance down here is, looking over here, the parallel combination of R2 and R3, whatever that is, call that R23, one resistor. You can replace these with one resistor, and then it's in series, and it becomes a series circuit, and it's in series with R1. Can you do this one down here? Using the nomenclature I showed you here, tell me what the total resistance is looking in from left to right there, and write it here. Stop the video and tell me if you end up what I ended up with. That's what I ended up with there. Let's take a look. Looking at this part of the circuit right here. I worked on the parallel combination here first, but if you look, I get R3 plus R4. That's in series, R3 plus R4. And that's in parallel with R2 plus the R1. Now you might have written it like this, which is okay. R1 plus, it's in series with the quantity R2 in parallel with R3 plus R4. Oh, don't forget those right there. Whoops. R4. Notice that we have the same equation here as we do here. I just tackled this part of the circuit first and then went to the R1 in series, or you could, probably prefer this way. It's easier to understand, I guess. It's R1 in series with R2, which is in parallel with R3 plus R4. On the next page, characteristics of parallel circuits. The voltage is the same across all parallel elements in the circuit. We discussed that. The total conductance, G sub T, is the sum of all the individual conductances. If they give you conductances here rather than resistances, it's 1 over 90 and 1 over 45 and 1 over 180, then you just, parallel circuits, you add conductances. And why do you do that? Because the total resistance of a parallel circuit is given by this equation. In the book, they prove that. We're not going to worry about it. But 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And this goes out to 1 over Rn, where N is equal to your number of resistors. That's all. By Kirchhoff's current law, the total current I at T is the sum of all the branch currents. The total value of two resistors in parallel is their products over their sums. So let's start looking at that in a little bit more detail. I'll show you a couple examples here of how that works. We're going to use this total resistance. We're going to use the concept of this Kirchhoff's current law, which we've discussed before, and we're going to explain how the total value of two resistors in parallel is their products over their sums. So let's go back and let's say we have two resistances. Let's say this is 200 ohms and it's in parallel with 200 ohms. And we want to know what the total resistance is looking in there, so we can get the total current. We have to know the total resistance of the circuit. We get the total current. Well, we know that 1 over RT is equal to, let's call this R1, and let's call this R2. It's equal to 1 over R1 plus 1 over R2. Getting a common denominator here and working this out, you'll find out that RT is just equal to the product over the sum of those resistors. That's all. You can use some algebra and go from there to there. A little bit of mathematics. So when you have just two resistors in parallel, it's the product over the sum. And if you calculate that, you're going to see you get 100 ohms. But you're going to notice something else. If you have two resistors and they're equal, the equivalent resistance of that circuit is like a resistor with just 100 ohms. It's 1/2. Well, that's what this gives you. This will give you 1/2 of any single resistor. If you have three of them, let's say you have a 60 ohm resistor in parallel with a 60 ohm resistor in parallel with a 60 ohm resistor. Let's do that one. You have a 60 ohm resistor there, you have a 60 ohm resistor there, and you have a 60 ohm resistor there, and you want to find the total resistance looking in. Couple ways to do that. First of all, after you work with a couple of these, you'll notice that RT, the total resistance of that circuit, the combination of all of those, they're equal, and there's three of them. It's 1/3 of in the single one. It's 20 ohms. It's equivalent to 20. But there's another way you could get that. In some circuits, they won't be equal like that. If you have 4, it's 1/4. If you have 5 in parallel, it's 1/5. But in some cases, this is going to be 50 ohms, this is going to be 20 ohms, this is going to be 10 ohms. But there's nothing wrong with doing it this way, taking this circuit and working backwards. Just find the equivalent of those two, product over the sum. So you can boil the circuit down to this. 2 resistors. Where this resistor, we're going to call it R prime, it's equal to the combination of these two. You can use product over the sum if they're not equal, or you can just see there's 2 resistors equal value. That's 30 ohms. So now you have 30 ohms in parallel with 60 ohms. So how do you boil that down one resistance? Well, now you can calculate our total as a product over the sum. Product over the sum, and it'll be 20 ohms. Either way you're going to get down to 20. Either way you get 20 ohms. What I would do, you're going to have situations like this. Let's put one more in. Let's make this 1.5 k ohms. Let's make this 2 k ohms. Let's make this 5.6 k ohms. Let's make this 10 k ohms. And I would use the 1 over RT on my calculator equals 1 over 1.5 k plus 1 over 2k plus 1 over 5.6 k plus 1 over 10k. This is the way I'd work it out. And what I'd do in my calculator is I would put 1.5 times 10 to the third, and I would invert it, plus 2 times 10 to the third, and invert it, plus 5.6 times 10 to the third, invert it, plus 10k times 10 to the third, invert it, and invert the whole thing. And you're going to get RT. You could combine these two here and get product over the sum, and then put that equivalent resistance with this one, product over the sum, and then take the equivalent resistor for these 3, product over the sum. You're going to get the same answer. So what I'm going to do is I'm going to grab my calculator here real quick, and I want you to do the same thing up here. Work it out a couple different ways, but I'm going to take 1.5 times 10 to the third and invert it. I'm going to take 2 times 10 to the third and invert it. Plus 5.6 times 10 to the third and invert it. Plus 10 times 10 to the third and invert it. And then I'm going to hit equals. Don't forget to hit equals so you get the total value for this. And then you just invert that. And what I get in this case, sort of a crazy answer, but this is what you'll get. Let's round it off to 692 ohms. You end up with 692 ohms. Try it different ways and see if you get that. And then finally, I want to mention here the current divider rule. This is, remember with series circuits, we had the voltage divider rule, and you have to memorize that and get it down. Pretty easy. The current divider rule, very easy. But it applies to parallel circuits. By the current divider rule, when 2 resistors are in parallel, the current of one resistor is the total current times the opposite resistor divided by the sum of the resistors. What do I mean by that? The current divider rule. Finding the current through any resistor or combination of resistors in parallel circuit can be reduced to a single step. Single steps are nice. So here's the proof of it. I have a simple current source here, and I have resistor R1 and R2. I call this I1 gone through R1, and I call it I2 gone through R2. We know that the voltage across those resistors is equal to the total current times the equivalent parallel resistance. In other words, if we reduce this as product over the sum and come up with one resistor, the voltage drop across this parallel circuit is going to be given by V of t. V of t is the current times that equivalent resistance. Okay, that's the voltage drop across each one of these. So what's the current through I1? The current through I1 is that voltage divided by R1. But look what happens. It cancels out the R1. When you put this expression in for V of t, the R1s cancel, we end up with an R2. That's sort of strange to students when they say you're calculating the current I1, and what's the current gone through this R1? What's I1 equal to? Well, it's equal to the total current coming in up here times the opposite resistor, R2, divided by the sum of the two resistors. That's the current divider rule. What's I2 using the current divider rule? It's the total current coming into the circuit, into the node point, times the opposite resistor you're trying to find the current in, times R1, divided by the sum. That's the current divider rule, and there's the proof of it. If you want to know the current gone through I1, it's simply equal to the total current coming in times the opposite resistor divided by the sum of the resistances. If you want to find the current I2, it's equal to the total current coming in times the opposite resistance, which will be R1, divided by the sum of the resistances. Let's do a quick example on page number 31. The current divider rule. You have 0.9 milliamps flowing into the node, and you have a 60 k ohm resistor and an 80 k ohm resistor. I want to know what I1 is. I want to know what the current is flowing down through the 60 ohm resistor, 60 k ohm resistor. I called it I1. It's equal to the current coming in times the opposite resistance. Well, the opposite resistance here is an 80. You have 40 up here. It's the opposite resistance branch that's in parallel with it. So it's times 120k divided by the sum of all of these, 180. It's 0.6 milliamps. What is I2 going to be over here? It's the total current coming in times the opposite resistance, which is 60. The opposite parallel resistance, which is 60, divided by the sum. It's 0.3 milliamps. And then you check your work by using Kirchhoff's current law at this node. The current coming in has to equal the current going out. Write the Kirchhoff's current law equation here, and if the sum of the currents at that node is equal to 0, then you know they're right. I'd write the equation there and do that. See example 218 in the textbook. This is a good example in the textbook. If you take a look at it, if you can't see that there, this is it right here. That's the example in the textbook. Example 218. I'd like you to read it and make sure you understand it. Couple ways of working that problem, but the author realized that those resistance values are equal, so you could use the product over you could use the current divider rule in this case. You could use the current divider rule, and it works fine to find the current in each resistor. But the author recognized that since the resistance values were the same, the current splits evenly. That's how he ends up with the 215. That's how he ends up with the 215 milliamps, because this 430 splits evenly because the resistances are equal. But if you use the product over this, if you use the current divider rule, you get the same value. You get the same value of current. Page 32, using the current divider rule on different circuit configurations. I want you to tell me what I1 is using the current divider rule here. And I want you to tell me what I3 is using the current divider rule there. I1 is equal to the total current, IT, times the opposite resistor, R3, divided by the sum of all the resistances, R1 plus R2 plus R3. What about I3? Well, I3 is equal to the total current, IT, times the opposite resistance, which in this case is R1 plus R2, divided by the sum of all the resistances, R1 plus R2 plus R3. That's current divider rule. What about in this configuration down here? What's I2 going to be equal to? What's I1 going to be equal to? I1 down here is equal to the total current entering the node, which is IT, times the opposite resistor, the opposite resistor to this is R2, divided by R1 plus R2. Down here, I2, the current I2 here, this current splits, by the way, like that. But if the resistance values are different, this is what you have to use. Total current coming in times the opposite resistor divided by R1 plus R2. What about down here? Have the current source over here, current coming in that direction. What's I1? Make sure you can do this. I1 is the total current coming in times the opposite resistors. In this case, there's two resistors divided by the total. And I2, the current I2 over here, is the total current coming in to that node, IT, times the opposite resistor divided by the sum of all the resistances. These are all examples of the current divider rule. And then finally on page number 33, parallel combinations real quick. What I'd like you to do is look E 4.2.14 over. You should be able to do this one, and this one in your head on page 33. Let's do them real quick. Do this till you understand it. This 3K and this 6K are in parallel. 3K plus 6K is 9K. The 9K in parallel with the 18K is 6K. So these can all be replaced with a 6K resistor. So 6K plus 6K plus 10K is 22K ohms. You did that one in your head. Let's do this one. We have the 4K and the 8K, which is 12K. They're in series. And that 4K and that 8K making 12K is in parallel with 12K. Okay? So you have 12K in parallel with 12K, which gives you 6K from here to here. Well, that 6K is in parallel with that 3K. Don't let this fool you. This could be a vertical here. So the 6K in parallel with the 3K is 2K. So 2K in series with the 4K gives you a 6K ohm resistor. Everything from here over, it looks like a 6K ohm resistor, and it's in parallel with 6K. That gives you 3K ohms. And then down here, you can do the same thing. These are all add up to give you a 6K resistor. That 6K is in parallel with this 6K here, which gives you 3K. So all this is 3K. And you take the 3K and you add it to the 3K, that gives you 6K. And you can work this backwards, and you can see you get 12K ohms looking in from the left. Up here, you get the 3K looking in from the left. And why are we trying to find these total resistances in these circuits? Because once we know the total voltage, we can divide by the total resistance and get the current flow here, getting the total current coming in there, or the total current coming in there. And then we can find these different branch currents. That's the next lecture. That concludes this lecture.